Okay, so now we're going to do some calculations with equilibrium. And we've done some calculations similar to this, and we called it stoichiometry. But now this is going to be related to an equilibrium constant. How much we're able to actually produce of both our reactants and our products is going to be related to an equilibrium constant. And we know that the more K you have, then that would mean that the more products you have, the greater the K, the more products, and the smaller the K, in fact, we've got that right here. The larger the K, the more products you have. The smaller the K, the less products or the more reactants you have. And in order to get this set up, we're going to do something known as a Rice table, which I'll show you in just a second. But also notice that sometimes you will come up with a value and where you've got something like x squared plus x plus a number. And in that case, you actually have to use the quadratic formula. You will see this on the homework, so we don't have any examples in our notes, but you should know how to do this from math. You can do it the long way, or we have a formula that you can put onto your calculator. So you can actually put the quadratic formula on your calculator as well, but you will see that on your homework. And our first example, now we said that we're going to be using something known as a Rice table, and what this is just a way of setting it up where we show um, R stands for our reaction, so we're going to rewrite our reaction. Then we're going to have the initial concentration, then the change in concentration, and then the equilibrium concentration is what we're going to show. So I'm rewriting my equation, my reaction. That's Fe plus 2 plus 2 FCN minus. And that's a reversible reaction. It goes to Fe SCN 2. So there's our reaction. I can read through here and I can even write down some information that I'm given. I see that I've got 2 molar iron 2 ions and 2 molar thiocyanate ions. So we can write that down. That is given to us. And we're also told that at equilibrium, so I'm going to draw my line here. There's going to be a change that takes place, but at equilibrium, we know that we have 0.6 molar FeSCN2. So that information is given to us. Maybe I'll even go ahead and put some squares around there, some rectangles to help you kind of remember what was given and now how we can go about calculating the rest of this. So the first thing I would do is I would say, well, as far as my initial concentration goes, I know that that's all I'm starting with are those 2 ions. So that must mean that I have 0 concentration or 0 molarity of my iron thiocyanate. So in that case, I know my reaction must progress in this direction in order to reach equilibrium. Now for the next part, for the change in concentration, it should be pretty obvious that we're going to have to add to this side and subtract from this side. So for our change in concentration, this information is going to be based upon your balanced equation. So it's based upon, let's say, mole ratios in balanced equation. What that means is that we know that when we add up FeSCN2 and everything that we've got there for the change, it's going to equal 0.6 molar. So that must mean we are adding 0.6 molar for our change, which means since this is a 1 and this value right here, I'm looking at my coefficients in my balanced equation, then that must mean we are subtracting 0.6 molar iron 2 ions from the left-hand side. And since this is a 2 and we're basing it on mole ratios, it's not going to be 0.6, but instead it's going to be that we subtract 1.2 molar. So that's going to be that 2 right here in our coefficient, times the 0.6. So this is a pretty important thing to remember, that it's going to be based upon the mole ratios. So now we can just do the math. 2 minus 0.6 gives us 1.4, and then 2 minus 1.2 gives us 0.8. And now that we have all the values of our concentrations at equilibrium, we can just go ahead and plug things in. So our equilibrium constant is going to be equal to, let me just go ahead and write down the expression first. Maybe, let's see here. Okay, so hopefully you can read that. So I've got my equilibrium constant expression written down. Now I can go ahead and plug in the values that we've calculated. And that's going to be 0.6 on top, and then 1.4, and then 0.8 squared. So when we go through the math, we end up getting our K value equal to 0.67. So that is your answer. Okay, so in this example, we were asked to calculate the equilibrium constant, is what we went for here. Next example. Here it's not the equilibrium constant, but we're asked to calculate molarity, or it might even just say something like concentration for each species, which we know to be molarity as well. So we're going to go ahead and set up our rice table. Reaction, initial concentration, change in concentration, equilibrium concentration. So our reaction is H2 plus I2 goes to 2HI. And give myself more space. Okay, so we read through the example, and one thing I see is that it gives me my K value. I'll go ahead and block that in. That's a given for us. And calculate the molarity of each species at equilibrium if 0.04 molarity HI is placed in a flask. So that's the only other information that we're given. Right there. So we can look at this and say that must mean that we have 0 concentration of these guys. So it's got to progress in this direction, meaning you've got to add here and subtract from this side. But we don't have any other values. We've got a K value, but we can't use that yet. So this is going to be when we have to use some X's in our change, and we're going to have to solve for X. But again, don't forget about coefficients. That's where it's going to come into play, is at your change. So when I look at my balanced equation, I have a 1, and a 2. So what that means is that this has to be a 2x, and these have to be x's right there. So when we go through and work this out, we get x, and we get 0.04 minus 2x. You know, another way, lots of times it makes it a little bit clearer also. If you want to do a double line, you'll quite often see this, a double line down here that separates your reactants from your product. So that's another option for you. So now that we have this all written out, we can go ahead and plug some things in. We know that our equilibrium constant expression would be our products raised to the power of their coefficients divided by our reactants. So now when we plug our values in there, I guess I can fit some here, we get 64 as our K value, and then we just start plugging some information in. And on this one, I'm going to get 0.04 minus 2x. That's my HI, and I'm going to square that. And then I've got x and x, so I'm just going to say x squared down here. So the easiest thing to do at this point is to just take the square root of each side. So you end up getting 8 equals 0.04 minus 2x over x. And then I'll keep working through this math. So you end up getting x equals 0.004. You're not done yet. Now what you need to do is you need to take that information and actually plug it in, because the question is, what is the concentration at equilibrium? So you have to take that value in and plug it in and say 0, actually let me go ahead and write the, okay, you've got to take your concentration of your H2, and that's equal to the concentration of your I2, which is going to be equal to 0.004 molar. And then your HI is going to be equal to 0.04 minus 2 times your 0.004. I should just do this in the calculator, which is equal to 0.032 molar. So those are your values that you've got right there. And that should do it on that type of question. Last one. Okay, so in this one, here we are, again, we're given the reaction and we're given a K value, but we have starting concentrations for both. So let's go ahead and set this up. You're going to need lots of room on this one. You've got your RICE, so again, same reaction. And we read through here, we're given our K value, and we're told that we have starting concentrations for HI is 0.05 molar, and it's going to be 0.027 for both of our reactants. So I'm not going to block it in, put blocks around there because I think it'll get too crowded. But we see that those are our original concentrations. Now, with our previous two examples, we were able to easily say, hey, it moves to the right or it moves to the left because we had zeros on one side or the other. But here we've got concentrations on both sides. So this is when a dilemma is reached and we need to figure out where we need to add and subtract from. So maybe we write that down. I'm not going to write it down, but you could say something like, if you're writing notes, you could say something like, because we don't know which direction the reaction will proceed, we must calculate Q. So that's the important information, is that we're going to calculate Q to determine direction. And so remember how to do Q. It's just like you do with K, but it's not at equilibrium. It just happens to be at initial concentrations instead. So our Q is going to be equal to our products of 0.05, and I'm going to square that because of my coefficient, and that's divided by my 0.027 times 0.027, so 0.027 squared. And when I go through this math, I end up getting 3.43. Well, remember, K equals 64. So what we end up seeing is that this is too small. So because it's too small, remembering that it's products over reactants, looks like since it's too small, I need more of the stuff on top. I need more products. I've got too much of my reactants. So need more products. Meaning it is going to shift, or it's going to proceed in this direction. So that's why we did Q. That's why we calculated Q, is so that we could determine what happens, which direction that reaction will proceed. Meaning that we are going to add here and we are going to subtract from this side. So I'll go ahead and do my double lines here if that makes it a little bit clearer, easier to see what's going on. So now what we can do is just go ahead and write in some x's, and this is just like the last problem because we've got the same reaction. So we know we're going to add 2x to the right hand side because of that coefficient, and you're going to subtract x from each reactant. So now you can go ahead and just do the math. 0.027 minus x. and then 0.05 plus 2x. And when you set this up, remember we know our k value, so I'm not going to rewrite. You can look at the problem from before to see what your equilibrium constant expression is, but you're just going to say that 64 equals, it's going to be your hi squared, so that's going to be 0.05 plus 2x squared divided by 0.027 minus x squared. And then you go through this. I'm not going to show you all the math for this. I think you guys can go through this and calculate it. But when you do, you should get x equals 0.0, I think it's 166. So you could probably just say something like 0.17. So that's what you get for your x value. And from there, what you can do is just say if that's x, now what you need to do is you need to take that value and you need to plug it in to your equilibrium values. So we end up getting for H2 and HI, no, I'm sorry, I squared, I2. For those two concentrations, they end up being the same, which is going to be 0.027 minus 0.017, so you end up getting 0.01 molar for each of those. And then for your HI concentration, it is plus 2 times 0.017. So for your HI concentration, you get 0.084 molar solution. You know, something I didn't mention, but hopefully you're catching on, is that you don't worry about the coefficients at this point. You've already dealt with the coefficients, so now you just plug it in because the coefficients are dealt with up here in the equation. So that is it. You now know how to do some equilibrium calculations.